I love it. You know what that music means? It's Morse Code of Weather time. Jacob is here. We're going to learn a lot more about weather radar. It's quite a series.
Yeah, well, I learned a lot last week, so see if you can top it.
Yeah, we went inside the radar last week. This week, we're going to be talking about how the radar takes a three-dimensional slice of the atmosphere a couple hundred miles out from the radar site. So if you remember from last week, the radar sends out radio waves, and as they propagate through the atmosphere, they interact with precipitation. The precipitation scatters those radio waves back to the radar. All this happens in less than a second from when the radar disseminates those radio waves, and then it receives it back and turns that into those radar images that we see. The problem is that the radar has its beam go up at a little bit of an angle. And with the curvature of the Earth, the farther of the way that you are from the radar, the higher up in the atmosphere that you're sampling. So if we look at the radar site over here, our radar beam going up, and it can miss sometimes low-level clouds. That's usually a common theme in the wintertime, where you have clouds that are a lot lower to the ground producing snow versus thunderstorms in the summer that are a lot taller. So the way that we assess how high the radar is scanning the atmosphere, we look at the elevation angle. We start at 0.5 degrees, and we go all the way up to 19 degrees in the atmosphere. And that samples the atmosphere three-dimensionally. So we can determine how far away the radar beam is scanning and how high up it is. So we go 1 mile up in the atmosphere for every 115 miles out that we are. What that means is when we go 115 miles out from the Bismarck radar, it takes us to about just east of Jamestown, near Minot, just west of Dickinson. So this is the area that we have the best coverage from the Bismarck radar, but we can get a little bit more data elsewhere, about 150 miles out from the radar. But again, it's sampling the atmosphere a lot higher up in those locations. So with the Bismarck radar, you can see westward we have less radar coverage just based on how high up the radar beam is going as it goes away from the radar site. And the height of the Bismarck radar also plays a role, because the height determines where that 0.5 degree elevation angle starts. The reason the Bismarck radar has to be 65 feet tall is because of the surrounding topography. It's a little, the National Weather Service radar is in a little bit of a valley down by the airport. For more on why the radar needs to be at a certain height and all of the different elevation angles, here's Chauncey Schultz with the Weather Service.
So when we're dealing with finer precipitation, lighter precipitation, say snowflakes for example, they're pretty small, so it's harder to detect that if the radar is spinning too fast. So the way we handle this is through what we call volume coverage patterns. So snowfall, for example, forms a lot closer to the ground than, say, thunderstorm clouds do. But we also know it's more sensitive, it's harder to detect. So we operate the radar in a little slower fashion, and it spins around more slowly, gives it more time to pick up on the small snowflakes, small rain drops when we're dealing with lighter precipitation. And then it might go up to 1.5 and 3 degrees slice above the elevation. There's no need to go really high in the sky when we're dealing with rain and snow, because all of that precipitation forms relatively near the ground. When we're dealing with thunderstorms, on the other hand, we know that the updrafts and thunderstorms are rising really to 50,000 feet in the worst case scenarios, and we know that the thunderstorms are developing, evolving very quickly. So in that case, it's more important for us to get a fast, full volume scan, is what we would call it in the radar, when it makes all of its revolutions and goes up in elevation scans. So during thunderstorms, we're going to employ what we call a volume coverage pattern that is faster, and it goes up from 0.5, and it adds more elevation slices too. So we're actually building a bigger 3D picture of the radar during thunderstorms. And again, we can control that as meteorologists from the Weather Service, what volume coverage pattern that the radar is actually operating in. And we do that based on the type of weather phenomena that we're expecting and that we're observing. If we're operating in that mode that is for snowfall or light rain, that takes about 6 minutes for a complete radar picture to be determined. If we're operating in thunderstorm mode, so we're spinning the radar a lot faster, maybe getting a little less fine details higher up in the sky, but we're going all the way high up in the sky and really getting those fine details of thunderstorms, it can be completed in about 4 minutes. And we actually have new technology with the radar where we can actually, halfway through its elevation slices when it's going up and around, drop the radar back down and scan that lowest elevation slice that's right near the Earth to get a sense of what might be going on with rotation in the clouds, potential tornadic activity right near the ground.
Thanks a lot, Jacob. Part 3 in your series coming up next week.